on black hole thermodynamics. And let's start by clarifying this notion of the killing horizon. Okay, so let's start first with an example. Okay, there's a simple example, that of the Schwarzschild method. Consider the metric ds squared is equal to minus dt squared f of r plus dr squared by f of r. Exactly the same discussion applies to Reissner-Nordstrom because I will use no property of f. Other than that, it vanishes at the horizon, plus r squared d omega squared. Okay. Now, I'm interested in looking at the vector del by del t. And I'm interested in explaining to you that this vector is a special vector at the event horizon of this spacetime. Okay? The problem with doing that in these coordinates is that these coordinates are singular at the event horizon. Okay? So, I know a nice set of coordinates in which the which are not singular at the event horizon. Okay, these nice set of coordinates are not Kruskal coordinates, which don't qualify to be called nice. Okay. The Eddington Finkelstein coordinates. Those are good coordinates, meaning they're usable. Okay, so let's look at the Eddington Finkelstein coordinates. Let's look at t is equal to v minus integral dr by f of r. The details again will not matter. Okay. In these coordinates, as you know, ds squared is equal to 2 dv dr plus f of r minus f of r dv squared plus r squared d omega squared. All this you know, we've gone through this many times. Okay. Now, you may be wondering, but you know, there's a problem. I wanted this vector. What I have is these v coordinates. But the great thing is that this vector is the same as d by dv. Why is that? We can establish this. Well, let's do it first in formulas. Okay, and then we'll do it in geometry. Okay. So what is d by dt if I transform to the other new coordinates? D by dt by the chain rule is equal to dv by dt at constant, well, r d by dv plus dr by dt at constant v del by del r. Sorry, at constant r. Right, I'm changing coordinates from it's 0. So let's see. Let's remember the general rule. The general rule is if you want to go from coordinates a, b to c, d. Suppose I want del by del a at constant b. That is the same thing as, according to the chain rule.
So tr to vr.
Tr to vr. Okay. So the point is that this is 0. Okay. Because at constant r doesn't change. Okay. And this is 1. Okay. And therefore dv, so d by dt is same as d by dv. Geometrically, why is this the case? It's because, what is d by dt? It's moving in t at constant all other coordinates. In particular, constant r. What is d by dv? It's moving in v at constant all other coordinates. In particular, constant r, because even in v, in the v coordinate system, r is one of the other coordinates. So, if you're keeping r constant, moving t and moving v is the same thing, because they differ by something which at r constant is a constant. Okay, so the little arrows corresponding to this motion are the same. So you understand that in the vector d by dt is same as the vector d by dt is same as vector d by dv. I'm interested, so these are the same things. It's sometimes nicer to think of the vector d by dt. For instance, because it's democratic with the future and the past. V is a good coordinate on the future event horizon, U is a good coordinate on the past event. T doesn't break that symmetry. It's bad in both. Okay, but this vector is the same. So okay, we're interested in the vector d by dt. That's the same, but we can analyze it by analyzing d by dv. Okay. Now let us look at what this vector d by dv is. Okay, d by dv is the vector that is 1 in the v direction, upper indices, 1 in the v direction and 0 everywhere else. I want to see what I get by considering dr, the one form dr, so the object with lower indices, which is 1 in the r direction and 0 everywhere else, and raising it. Okay? In order to do that, I need the upper metric, the inverse metric. And let me actually do it where I want to. I want to do it only at the horizon. So I want to do it at a place where f of r is equal to 0. Okay? So then it's clear that when I raise dr, I get something only in the v direction, because the metric is 1, 1, 0, 0. So its inverse is also 1, 1, 0, 0. So dr is raised to dv. So you see that this object, which at the event horizon is the normal to the event horizon, because the event horizon is this manifold r is equal to rh. Rh is a constant. So d of that is dr. So it's a normal one form to the event horizon. When we raise its indices, we get the vector field d by dt, d by dv, which is the same as d by dt. Okay. Notice that d by dt was a Killing vector field. Okay? So what we've just realized is that in the case of the Schwarzschild black hole, okay, what we've just realized is that in the case of the Schwarzschild black hole, the horizon is a Killing horizon. What that means is that the normal vector to the horizon is the restriction of a Killing field. Is the restriction of a Killing field which exists in all of space-time, but to the event horizon. This is clearly a Killing field, right? Because the metric doesn't depend on t, it doesn't depend on v. Is this clear? Now this is a general property of all stationary black holes. Oh, all is very strong. All stationary black holes in 4 dimensions. There are exceptions. All these things are, these theorems all are untrue in general. Okay. I want to now go through a similar analysis, which unfortunately will be much more complicated.
Sir, I have one number.
Yes.
Here is the normal to the surface.
It's the normal to the
Of the horizon.
yes.
And if you raise it this vector, then you get the del V.
Yes.
And what is the statement?
Now consider d by dv. This is a vector field that's well defined all over spacetime. If we consider the restriction of that vector field to the event horizon, it agrees with the normal. So the statement is that the normal, that the generators of the normal are the restriction of a Killing vector field in spacetime onto the event horizon. This is only true, of course, in stationarity. Black holes, dynamical black holes, have time-dependent event horizons. And the normal vectors, the generators of this event horizon, are not the restriction of any Killing vector fields. Precisely, basically the statement that nothing is happening in time. Okay? But it's an important statement. Okay, so I'll say it again, that the generator, think of the event horizon. It's made up of these, it's generated by these null generators. Like these geodesics that thread the event horizon and whose union makes up the event horizon. It is possible to extend this vector field, the vector field of the tangent vectors of the event horizon, to all of space-time in such a way that it is a Killing field. And that extension here is d by dt.
These are not the null generators.
These are the null generators at the event.
At the event horizon.
Everywhere else they're not null.
dr on the horizon is the null generator.
Is the null one form?
Null one, yeah.
Now you raise it,
Part of this
is d by dt.
and you can continuously take out of the horizon to be as a killing field.
As a killing field, as we've seen, because that's d by dt. Okay? So that the event horizon is a particular slice of a killing field. The generators of the event horizon, the tangent vectors of the event horizon are a particular slice of a killing field. Is this clear? By the way, we'll see this soon. There are two natural normalizations of the tangents to the event horizon. One natural normalization is the normalization that's affine. This normalization we encountered in our last class. If you just take the event horizon to be the equation S is equal to 0, okay, such that del S, the whole thing squared, is equal to 0 on the event horizon, then del mu S gives you the tangent vector such that you obey the geodesic equation without any right hand side, which means that it's affinely normalized. So this affine normalization, this is one natural normalization. There's another natural normalization which is, let it the normalization such that it agrees. You see, now the killing vector field in all of space-time has its own normalization. Because overall normalization, multiplying it by constant doesn't matter. But relative normalizations are completely fixed by the requirement that it's killing. If I take f of r times d by dt, or f of theta times d by dt, it's no longer killing vector field. Okay? So there's another natural normalization up to constant, which is that of the killing vector field. And you can ask, are the two the same? And the answer is they're not the same. Okay? And the relationship between them will be an interesting relationship. We'll come to by the end of this lecture. The constant of proportionality between these two will be related to what's called the surface gravity of the event horizon. Okay? But we'll come to that. Let's go slowly.
Killing vector field at the event horizon is normal.
Is proportional to the normal, yes.
So why is it take killing vector of the delta gravity? There is another killing vector.
In the case of the curved black hole,
Yeah, in this delta delta.
del by del phi is also a killing vector field. But there is only one killing vector field which agrees with the generators of the horizon, which when restricted to the event horizon becomes the generators. And that, as we've just seen, is del by del phi.
Delta delta
Is not, it is a killing vector field, but it's not the distinguished one for this black hole. Because when you take del by del phi and restrict to the event horizon, it does not agree with the generators of the horizon. So there could be zillions of killing vector fields, or a few. But there's only one which, when restricted on the event horizon, agrees with the generators. This is a distinct, up to overall constant. Yeah. Yes?
Del mu S won't be a killing field.
What? Del mu S will not be a killing field. Yes. Okay. Any question?
Directionally, they can be identical.
Directionally, they'll be in the same direction, but the proportionality constant will vary as a function of position.
Yeah. I mean, some position dependent function of.
Yes. Okay. So let's keep going. Now, all of this was very easy with Schwarzschild or Reissner-Nordstrom black holes because the formulas are so easy. All of this is much more painful with the curved black hole, but let's roll up our sleeves and do it. Okay. So what we're going to do, what we want to do, in order to go through this kind of analysis, we need a coordinate system for the curved black hole that is non-singular on the event horizon. And we want to be able to work with this coordinate system, so we don't want some abstract bullshit about this and that. We want formulas, proper, so something like this. This Eddington Finkelstein coordinate system. Okay? Now I probably didn't even present it to you this way. Did I? I probably didn't. didn't even tell you this. Let me. Did we discuss that lines of constant v are ingoing null geodesics? We did, right? Okay. So the Eddington Finkelstein coordinates are, you see, one way of thinking of this coordinate system is imagine a bunch of ingoing null geodesics, a distinguished bunch of ingoing null geodesics going into the black hole. Okay? It's distinguished because these things are falling radially into the black hole. The null geodesics could go in any direction. But we're looking only at radial null geodesics. Okay, that completely determines it. Because as you know, in an effective two-dimensional problem, if you're null, that completely determines the line. Okay? This, in Eddington Finkelstein coordinates, it's clear that lines of constant v, theta and phi are null because there's no term in the metric that has a dr square. So v is constant, theta and phi are constant, everything is 0. Because everything is proportional at least 1 dv or d theta or d phi. So if they're all constant, you get 0. So lines of constant v, theta and phi are null. In fact, they're null geodesics. Okay? So this coordinate system was based on, geometrically speaking, was adapted to a congruence of null radial ingoing geodesics. So if we want to find a good coordinate system in something in which we will see the future event horizon being nice, in the case of the Kerr black hole, okay, we should find, well, if we want some generalization of the Eddington Finkelstein coordinates, we should look for a set of null, in a distinguished congruence of null ingoing geodesics. Okay? I'm going to try to find such a congruence for you. Okay? I'm going to do it, only partially deriving the equation. By which I mean I'm just going to, there's a bunch of equations that you get from studying the geodesic equations, and then you simplify using various tricks. Two of the tricks are using the fact that energy is conserved, that translations in T is a symmetry, and translations in phi is a symmetry. That helps you simplify the equations. Actually, there's one more symmetry in this Kerr geometry, which is harder to see, and I will not talk about, which helps this problem to become solvable. Okay? You see, we lacked the symmetry of rotations on the full two-sphere. That's what helped us to solve, let's say, geodesics in radially symmetric situations. Okay? But there's another new mysterious symmetry, which I could give you references for if you want. Killing fun or something. It's got some fancy name. Okay? Which allows you to integrate the geodesic equations completely. Of course, if you didn't know this, you would integrate it anyway after more work. Right? But in the end, when you write down the null geodesic equations, you get the following equations. I'm just going to write them down and then we'll look at them. So we're working in the coordinates we've always worked in so far. These are theta phi coordinates. In those coordinates, I want to find the geodesics, and then I'll use them to change coordinates. Okay? So the equations turn out to be rho squared T dot is equal to minus A into A e tilde sine square theta minus L tilde. I'll tell you what everything is. Let me write it down. Plus R square plus A square P by delta. Rho squared. What?
No,
P. I'll tell you what P is. R dot is equal to plus minus square root of R. I have to tell you what capital R is also. Rho squared theta dot is equal to plus minus square root of theta. And rho squared phi dot is equal to minus A E tilde minus L tilde sine square theta plus AP by delta. Okay, where P is equal to E tilde R squared plus A squared minus AL tilde. R is equal to P squared minus delta L tilde minus A E tilde, the whole thing squared, plus, okay, he's used some funny notation, let's call it Q, no, zeta. And theta, okay, this is also, you will confuse it with this, so let's call it I don't know, mu, B, I got a mu. Is equal to, what do we call zeta plus cos squared theta A tilde squared L tilde squared pi sine squared. Okay. And E tilde, L tilde and zeta are constants. Okay, let's look at this for a minute. Zeta, that's the zeta. Zeta, whatever, call it what you want. Yes. So you see, what we've done is take the geodesic integrations and done 3 first integrals. Okay. More simply, this is just the energy. This is just the angular momentum, and this is the charge for this other mysterious symmetry that I'm not going to tell you about. Okay.
Is it something like the Rungelen's vector in the Cambridge problem?
Mildly. There's a tensor associated with it. Rather, yeah, a killing tensor field. Yeah, exactly. Okay. It's sort of interesting, and as far as I know, there's no equivalent of it in higher dimensions. Sort of accident of 4 dimensions. But it's very nice because it allows you to do things explicitly. Okay.
So this is sort of an accidental symmetry.
Yeah, I mean, you know, you never know when something's accidental or not. So if you're deep enough, you see it, but it's not immediately visible to the untrained eye. I mean, the other two are immediately visible, right? There's no, and in particular, there's no killing vector associated with this. These are the only 2 killing vectors in the geometry. It's not like there's a 3rd killing vector. Still, there's a symmetry. It's a quite subtle thing. Okay. Fine. Okay. Now, we've got everything explicit here. Okay. We've got our geodesics. We've got our geodesics here labeled by 3 parameters. That's reasonable, right? Because you take some 3-dimensional cut, and you've got a geodesics come in a 3-parameter set if they're going to fill up a 4-dimensional space. Right? Because a 3-parameter set of lines fills up a 4-dimensional space. So it's reasonable that we've got geodesics labeled by 3 parameters. Okay? And we'll see that more explicitly. Okay. So now what we are going to do is the following. You see, these are very complicated equations. Everything is moving. Dot, by the way, is of course motion in affine direction, with respect to affine parameter. Okay, so with some choice of normalization. Okay, so everything is moving. Now, because things are rotating in phi, you expect things to move in phi. Of course, everything moves in time. You expect them to go inward in r. But you might hope that it's possible for things not to move in theta. That would be very nice, right? So let's see if that's possible. So the way that theta will not move is if mu is equal to 0. Now, let me put this right. Suppose I choose, suppose I do the following. Okay? Suppose I choose L tilde is equal to A E tilde sine square theta, and mu is equal to minus L tilde minus A E tilde, the whole thing squared, which is equal to minus A E tilde cos square theta. Now when I first write this down, you're thinking this makes no sense. This makes no sense because I told you that L tilde and E and mu were constants, but now I've got thetas in these equations. Sorry, psi. Xi, the constant. What? Yes, thank you. This one, that's what you were saying, right? Yeah. Okay, excellent, yes. So when I first write this down, it looks like it makes no sense. Right? For instance, the relationship between L tilde and E tilde, what does it mean if it's I mean, it's either it's a constant or it's dependent on theta. But precisely these choices of constants, these choices are constants that are going to make theta constant.
So, question, will there be an A square before E tilde square?
Yeah?
No, in the last equation, mu.
Let me check. Yes, you're right. Thank you. Okay? Precisely these choices set this mu to 0. Okay? This you can easily check just by plugging in. Okay, what you have to do is plug in what
But
L.
this is not a unique choice, this is one choice.
This is a choice I'm going to make. Yes. Just plug in and you'll check. Okay? It's 2 minutes. Check that with these choices, mu is equal to 0. Okay? So now if mu is equal to 0, theta is a constant. And so now our geodesics is greatly simplified. They move in,
Constant.
yeah,
On L.
they sit on a particular theta. They move in phi. They rotate. Of course they rotate. They move in time. They move in r. But they sit at every theta separately. A particular what? They are valid only for, no, for every theta. Yeah. So now we're going to move our parameters. Okay? Our geodesics will now be parameterized by theta. Let's say I'll parameterize my geodesics by E tilde and theta. And of course I'm starting phi, which will make no difference. Okay? Now,
Changing different initial condition particles from different theta.
exactly. I choose different L tildes for different thetas. And choose different zeta tilde. Let's say I fix E. For fixed E, I choose a different, depending on which theta I'm at, I choose a different L tilde. Okay? For every value of L tilde, E tilde, these are
This
geodesics.
is space-time filling congruent.
Yes, I'm going to generate a space-time theory. This was just the geodesic equation. Anything that satisfies this for any values of these constants is a geodesic. Okay, so I'm free to choose the constants to move, to change as I move around. Okay, so I make these choices. You can call it theta naught if you want, but I'll ensure that theta naught is equal to the theta that the geodesic stays at, and then it'll stay at that theta forever. So because thetas are constants of motion, the geodesics are now labeled by theta, as well as by this E tilde. They're also labeled by starting phi. But since nothing depends on that, we don't really see that in the equation.
So in other words, on all these space-time filling geodesic congruences, we are looking at geodesics which are constant theta.
Yes, that's a huge simplification of the problem. Is this clear? Okay. So now with these choices, okay, with these choices, what do we get? Firstly,
that term in T dot vanishes, the first one.
Yeah. Firstly, as you said, that term in T dot vanishes because L is equal to A E tilde sine square theta. Okay. So we get rho squared T dot is equal to R squared plus A squared P by delta. Now we can even simplify. Anyway, we can plug in everything here. Like L, I'm not going to do this in too much detail. We get R rho squared R dot is equal to plus minus of this R. This is the whole thing is 0. Excellent. Is equal to plus minus P. And we get rho squared phi dot is equal to AP by delta. Is that right? This whole thing
That's A
is
is the sine to the fourth theta. And A is AE sine square theta.
that's correct. It's whatever it is. It's something. Okay. It's something. I'll check what. He gets T dot is equal to E by. Okay, now we have to evaluate what this rho squared was. Okay, let's do one of these, and I'll. Yeah, where was what was rho squared? Just a minute. Rho squared was R squared plus A squared cos squared theta. And P and delta we know. Okay, delta I'll have to report. We've forgotten. Delta was R squared minus 2mr plus A squared. Okay, let me try to simplify this one, for instance. And then I'll just quote the results. Okay, so T dot is equal to R squared plus A squared into P, which was E tilde into R squared plus A squared and minus A times L. So minus A squared E tilde squared sine squared theta. Minus E tilde A squared
AQ.
squared theta.
Oh no, sorry.
Right. Okay, so E tilde here is common. R squared is whatever it is, and A squared minus A squared sine squared theta is A squared cos squared theta. And that is rho squared, exactly. So this is R squared plus A squared cos squared theta, but that was rho squared, and we had rho squared downs. we had rho squared downstairs because, yeah, divided by rho squared. So this just cancels this. Okay?
And there was a delta.
And there's a delta. You're right. So delta is what it is. R squared minus 2mr plus a squared. Okay. So T dot is this stuff. Let me check. Exactly. So T dot is this stuff. I'll just continue to write this as E tilde R squared plus A squared over delta. Similarly, if you simplify the other guys, you get R dot is just plus minus E tilde. This should be easy to see. Yeah, because this was just this stuff. E tilde R squared plus A squared, and then R squared plus A squared was rho squared. Okay, so R dot was just plus minus E tilde. We see that immediately. And the last one, maybe a little more work, is phi dot is equal to minus A E tilde cos squared theta, the whole thing squared. What? Is a constant, exactly. This is a constant, but this one is not a constant. Oh, wait. Sorry, did I get I'm sorry. You're right, I quoted this wrong. Sorry, I was reading the wrong line. It's not a constant, it's a function of R. A E tilde, I wrote down the formula for psi by mistake. By delta, yes. This is not a constant because delta is a function of R. Okay, I'll write down, just for uniformity, I'll also write down the T dot. T dot is equal to E tilde R squared plus A squared over delta. Okay? Good. Now that we got this on the board, I'm clearing everything else out. Now, the next thing we do, okay? Now the next thing we do is define the following coordinates. Let us define V is equal to T plus integral R squared plus A squared over delta dr. And psi is equal to phi plus integral whatever appears here. A by delta. Yeah, there's a sign made. What have I got wrong here? There's something here. I've got phi dot is plus. Oh, see, I got that wrong. Plus. Yeah.
If that has to happen, then maybe this combination is
Which one? Sorry, I'm sorry about this.
transfer.
This one? Ah, you're absolutely right. Phi dot. Oh, sorry, wait. Let me just go straight. Phi dot. I'm sorry, people. Okay, that's by L tilde by sine square theta. Sorry about that. Okay. Now what is the point of these definitions? What is the point of these definitions? Let's write this vector here as the following vector. Okay, let's write this vector as the vector. Okay, but firstly, the first thing we're going to do is to rescale our affine coordinate parameter to get rid of this irritating E tilde. Because it appears everywhere, it just gets rid of it. The second thing we're going to do is to choose the minus side, because we want ingoing geodesics, so that R decreases as affine parameter decreases. And so this can be rewritten as R dot is equal to minus 1, phi dot is equal to A by delta, and T dot is equal to R squared plus A squared over delta. Okay. So this tells us, this gives us the tangent vectors along the geodesic. What are the tangent vectors in nice geometrical notation? So it's minus del by del R plus A by delta del by del phi plus R squared plus A squared by sigma by way of delta del by del T. This is the vector field of the tangent vectors of our null congruence. Because it's tangent vector for each of them. Okay, notice the fact that there's no theta tells us that it's moving along constant theta. Okay, now once I've made this change of coordinates, the point is that in the coordinates, if I move to coordinates r, v psi, okay, let me see, okay, in these coordinates, claim this is simply the vector del by del r. How do you see that? Well, del by del r is del by del r by del by del r. You know, we're moving from RV psi to R T phi. Exactly. So this was del by del r at constant V psi, and now
That's at constant T.
exactly. This is at constant T phi, and then del by del r again at constant. No, so this was at V psi, and this is at constant T phi plus del r by by del r by del. Now I move to the new
Del D by del R.
del, exactly, del T by del r,
Del R.
because I'm moving to coordinates here. Del T by del r, del by del T. I'm not bothering to write down what's constant, right? You know, okay, plus del phi by del r, del by del phi. Okay. Now, having said I was not bothering to write down what's constant, let me just do it for these two because we'll evaluate them. So this was at constant V psi. Everything's at constant V psi. So now all I have to do is, in order to see what the vector field is in the old coordinates, all I have to do is evaluate these. This is clearly 1, so that's del by del r. Okay. But now what about these guys? This is del T by del r at constant V psi. So what I'm supposed to do is to write T as a function of everything else. So I take it to the other side, so there's a minus. Then I differentiate with respect to r. So that gets a minus r squared plus a squared by delta. So that gives me minus of this and minus of this. So up to an overall minus sign. You see that that works? Is this clear? So now this defines the change of coordinates. So now what we're going to do is to write down the Kerr metric not in the coordinates rt phi but in the coordinates rv psi. Notice, and this is of course the key point, that delta goes to 0 at the event horizon. So this change of coordinates, which is innocuous everywhere away from the event horizon, is singular at the event horizon. Does it mean that it's a coordinate change we're not allowed to do? Of course not. Because that's the whole point, right? We were viewing the event horizon in singular coordinates. The only way we can desingularize that is doing by a coordinate change that is singular relative to the singular coordinates, so that we go to regular coordinates. If it hadn't been singular, we'd have to worry, because we know that it couldn't remove the singularity of the event horizon. Okay? So now, this part I'll leave for you as an exercise. Plug in the change of coordinates and show that the Kerr metric becomes I'm clearing all this.
dr d psi, right?
dr d psi, yes. The new elements in this thing, compared to Eddington Finkelstein metric for the Schwarzschild black hole are this term and this term. There were no analogues of these two terms. Okay, and you see that both these terms have come proportional to an A. So you said A is equal to 0. This will just go over to the usual Schwarzschild metric. Okay, in Eddington Finkelstein coordinates. So this is the Eddington Finkelstein version of the Kerr metric. Okay. Now that we have this, we have the Kerr metric in good coordinates in order to study the future event horizon. Okay. So now, next exercise. Okay. Show that del by del t, but because that's at constant r, it is the same as del by del v, just like as it was for the Schwarzschild. Okay, minus omega of r plus del by del phi, because it's a constant r, it's the same as del by del psi. Okay, so though I'm saying del by del t and del by del phi, when you actually show it, you'll use del by del v and del by del psi. Okay, this is clearly a killing vector field. It's proportional to dr raised at the event horizon. dr, as you remember, the event horizon was r is equal to r plus. So normal to the event horizon also for the Kerr solution. Note r hasn't changed in these coordinates. So r is equal to r plus is the same equation. Okay, the normal to the event horizon is just dr. Okay, you have to raise dr. So you have to be a bit careful because there is this and there is this. Okay, so you have to raise dr a bit carefully and show that exactly agrees up to some proportionality with this field at the event horizon. What does that mean? It means that the generators of the horizon of the Kerr black hole are also the restriction of a Killing vector field to the event horizon. Except that this Killing vector field is an interesting Killing vector field. You see, this Killing vector field, is defined all over space-time. So we can look at it in infinity. Inside the strange metric intuition breaks down, but at infinity we're in flat space. We can ask, what was the Killing vector field there? And it was, as you went up in time, you went round at angular velocity omega. Okay? So instead of just going, it's the vector field that's not just going up in time, it's going up in time and rotating. As you go up in time, you rotate. So there's a rotation that this Killing vector field, which at infinity reduces just to this advancing in time and rotating at a particular angular velocity, is the Killing vector field which at the event horizon agrees with the generators of the event horizon.
So the Killing vector field of which this is a restriction is ddt minus omega r.
R plus.
No, even at infinity. So the Killing vector field of which this is a restriction. When this is restricted, this is r plus.
No, but it's always r plus. You see, it wouldn't be a Killing vector field if this was a function of r.
I see.
Omega r plus should be thought of as a constant.
I see.
Okay? To emphasize that, people sometimes call this omega. H.
Okay.
Omega horizon. It's just a constant
Yes,
there.
Yeah, I mean,
Yes.
no restrictions.
Yes. So the restriction, this field is this with this constant. That's a number. That's very important.
And that is a Killing vector at infinity also.
It's a Killing vector over the whole space-time.
Yeah.
Right? Because d by dt is a Killing vector in space-time. d by d phi is a Killing vector. Therefore, any linear combination with a constant
Yes.
is a Killing vector. Is this clear? Excellent. So we've checked in the Schwarzschild case a very beautiful property of black holes that is true of a very large variety of black holes. I won't say everyone because there are always these small exceptions, but almost all known black holes. Okay? And there are some formal proofs, but these formal proofs always make assumptions. Okay, at least in this case we've checked that these Killing vector fields, that the event horizons of this particular Kerr black hole are the restriction of a Killing vector field. Okay, so at least in this case now we can use that fact. So let's use it. Okay, so consider the quantity so this Killing vector field, whatever it is often called zeta mu in discussions in black hole physics. Okay? Now let us look at the quantity zeta mu, and consider the covariant derivative of this. Now at first you might be thinking, well, looks like it's trivial because didn't we check, wasn't this Killing vector field null? But remember, that's only true at the horizon. This quantity we're computing in all of space-time. It's not a trivial quantity. Okay? So as you say, I will evaluate this only on the event horizon. But remember, the variations can be away from the event horizon. So it's not a trivial quantity. But what I do know is that if I have any tangent vector, say I evaluate this at the event horizon, and I dot it with any tangent vector along the event horizon, then I get 0. Because along the event horizon,
This
it's just 0. We're differentiating 0. So what does this mean? What vector has the property which such that when dotted with any tangent vector on the event horizon,
and that's itself the event horizon that will be
and therefore it must be that this is equal to some constant
then T alpha.
times zeta alpha,
Okay.
because zeta alpha reduces is proportional to the generator. Is this clear? Let me check I've got the factors of 2 right in my equations. Minus, they want a minus. Yeah, apart from that I've got it right. Let me just make sure. Yeah. Okay. Now since what? This is true only on the event horizon. Evaluate this del is del over all of space time, but after I've taken the derivative, I'm evaluating the derivative at the event horizon. Okay? Now this of course I can evaluate by chain rule. Okay, so that's zeta. This is minus zeta mu del alpha zeta mu is equal to no 2 now kappa zeta alpha.
Yeah.
But remember that this was a killing vector. Okay, because it was a killing vector, you can exchange indices. So that is, and I get rid of the minus sign. So I get zeta mu del mu zeta alpha is equal to k times zeta alpha. Now this equation tells us something that we already knew. It tells us that zeta is a geodesic, obeys the geodesic equation. But notice, not necessarily in the normalization, zeta is not normalized so as to be affine parametrized. Okay? However, the normalization of zeta is not in our hands. I mean, you can't change it because it's a killing vector. It's whatever it is. Okay? So this equation gives us something like this with some k. We can't control it. Okay? Now, this k is a very important quantity in the study of black hole physics when we're looking at stationary black holes. And it has a name. It's called the surface gravity. Okay? We're just going to evaluate it for the... there are formal proofs that within stationarity, this k is a constant along the event horizon. Actually, the proofs are surprisingly hard proofs. It's relatively easy to show. Let's give that as an example. We're going to evaluate it. So for the square black hole, we just see it. Okay? But you know, people like to do these formal things so that they might apply to more general black holes. Okay? Okay, I'll give it. Let's do some exercise. Show that kappa is constant along a geodesic. I mean, which means that zeta dot del of kappa is equal to 0. This is relatively easy to show. Actually, it's very easy to show. But you can show this. The harder proof is that zeta is kappa is also constant as you run between geodesics. Yeah, there must be a better proof than I found. The proofs I found in the literature go back to the bifurcation surveys. All anyway, I'm sure there's a better proof. I have not seen one. In fact, one of the textbooks I read said it's surprisingly difficult to prove this statement. Maybe one of you can come up with a good proof. It's probably anyway. I haven't seen a good proof of this, but it's true. You can prove it in a very convoluted way, and we're going to just check it by evaluation. Okay, we've got a clear definition of kappa, so we can just evaluate it. Okay. So let us check. Find it here. Show that kappa is equal to since every quantity here is a constant. Remember what R plus was. It was the outer zero of delta, which we evaluated by solving some quadratic equation. So it's all very explicit. Okay, here in this case it's clearly a constant, which means, for instance, it doesn't depend on theta. Clearly it didn't depend on phi. Phi was a symmetry.
So in that statement, kappa is a constant along given kappa. Was the non-trivial part of that proof applied to this case?
Yeah. So the non-trivial part is to show that this is independent of theta. Okay. You see, these geodesics stay at constant theta.
Yeah.
Okay. But this kappa here could have been a function of theta. It was clearly not a function of phi. That was symmetry. And clearly not. There's nothing else could have been a function, but it could have been a function of theta. The fact that this evaluates something independent of theta is non-trivial. Okay? Excellent. Now we're going to go back to the exercises I tried to list at the end of the last class. And now that we know everything about the quantities we're talking about. By the way, the fact that this kappa is non-zero tells us that the normalization of the Killing vector on the horizon is not the same as the normalization of the affine parametrized geodesics. And in fact, going from one to the other, anyway, there's some connection with Kruskal coordinates, but I will not talk about that. Some of you may know this. Please. You can change the parameterization, but you say zeta was a Killing vector field.
Yeah, this will not be a Killing
And
vector.
that fixes the parameter, that fixes zeta up to an overall constant. On the event horizon, of course, we're free to change the parameterization. But zeta was a
restriction of
was a particular Killing vector field defined in all of space-time and completely fixed by the fact that it was Killing. Okay?
But sir, up to constant.
Up to a constant. And that
kappa is a function of space.
kappa is this.
It is space. But
If I change this, it will change by a constant. But then the Killing vector field will no longer you see, what we have done is chosen the Killing vector field so that it's at infinity is d by dt with a factor of 1. Okay? So this is going to be we'll interpret this as dual to a temperature. As a temperature. Now temperature is dual to a particular energy. If you change your definition of time, you're changing what your energy is, and therefore you change your temperature. Okay? So this kappa shouldn't be too constant. It has exactly the right variation that it should have. Okay, great. Other questions, comments? Okay, fantastic. So now I will relist the exercises we tried to list at the end of the last class, but now that we know everything about the quantities, the exercises will make complete sense, hopefully, unless we discover something else we don't know. Let's see. So exercise. Prove Smar's formula. Or check Smar's formula. In the general relativity community, when you use the word proof, it should be abstract. Here we're just going to check Smar's formula. Oh, sorry. This by 4 pi.
No, this is 2 omega j?
2 omega r plus j.
Yeah.
Okay? Actually, the exercise before this should have been check that the area of the event horizon
Yeah, that
is equal to 4 pi
r plus square plus h square.
plus h square. Okay? And the last thing I want you to check
Variation.
was the variation. I'll just write that down. Okay. This formula is some formula. This formula is very important. Okay? Now firstly, let's look at the logical status of that formula. Okay. I've got a 2-parameter set of black holes labeled by M and A. So if I change A and M, I will change capital A, I will change capital M, and I will change capital delta. Both of them are proportional to variations of delta A and delta M. And therefore, there is one relationship between them. The 3 quantities linearly dependent on 2 variables, there has to be a relationship. Okay? So there has to be a linear relationship between delta A, delta M, and delta J. Because there are only 2 things to vary, and there are 3 variations. That there exists such a thing is not surprising. What is sort of nice about it is that the coefficients turn out to be very nice. Okay? This is just the mass, and this is minus omega times the angular momentum. Now, as I started saying in the last lecture, this expression here reminds us of the following relationship. Okay? This is a relationship from thermodynamics. This is the relationship from thermodynamics for what? Consider, let's say, a quantum system. Okay? Consider a quantum system such that you define the partition function of that system to trace e to the power minus beta h minus omega j. Beta is 1 by 2. Okay, so now this is an aside, okay. Everything here was just general relativity. Now I'm trying to explain to you where, just in case you don't remember your thermodynamics, where this comes from. Okay? Now, let us see. This expression in a thermodynamic limit can be thought of as integrating over all energies and angular momenta. All dE dj times e to the power s of E and j. Okay, because that's the total number of states in the range E and j, minus 1 by t minus E by t plus omega j by t. In a thermodynamic limit, that's what that partition function is. Okay, and where does this partition function get its maximum contributions from?
From the saddle point.
From the saddle point. Okay. Now, where is the saddle point? We have to take this expression and vary it. So that is that tells us that delta S, which is a function of E and J, I should really, yeah, this should be derivative with respect to both D, E and J. So I'll just write that as delta. S is a function of E and J minus delta E by T plus omega by T delta J has to be equal to 0. The saddle point condition for the evaluation of this partition function is this, which is the same as this relation. So on the saddle point, on the definition of thermodynamics, this relationship is obeyed. Just the saddle point condition for the evaluation of the partition function. Okay, so if you were interested in evaluating this for a quantum system or a classical system, the way I've written this for a quantum system, okay, in a thermodynamic limit, you would evaluate it on a saddle point which would obey this equation of motion. So we see that on saddle points, which, you know, it's the saddle point condition that relates the entropy, energy, and J, which in general are three independent things. But the saddle point condition relates them to give entropy as a function of E and J, and therefore to obey a relationship like this. Is this clear? Okay. So this expression here looks sort of like this, because clearly m is the energy of the black hole that we've seen. J is the angular momentum of the black hole. Omega looks pretty much like omega. Because it was the speed at which this d by dt was moving, this thing was moving at infinity. Now why is that related to this omega? For that you need to do a Euclidean continuation.
So this is what I always wondered. I mean, when we Euclideanize our metric, t gets to a minus dt square to plus dt square, but our d pi square was always positive to begin with.
Yes.
So, and what does that Euclideanization come from?
Sorry, say again?
No, I mean the Euclideanization of the time coordinate gives us the temperature.
Yes.
So, but correspondingly, the angular momentum or the angular velocity.
You don't need to Euclideanize that. See, why did you need to Euclideanize time? It's because this trace, when rewritten in terms of a partition function, is a partition function written over Euclidean time.
Yeah.
There's only one Euclidean thing, the thing that generates the trace.
Yes.
Okay? So this has to be, it's time that has to be Euclidean. And then that was already what it was.
So that doesn't come from any Euclideanization?
No. It just comes from, I mean, this thing here tells you that when you do the trace, you have to do a rotation. Right? Because J is the generator of rotations. Okay? So what you see, when you do a trace like this, what does it mean? Imagine doing the Feynman trick to convert this into a path integral. So what you will do is insert a complete set of states all the way through. Now, the initial state will be identified with the final state. Suppose we didn't have this. You would just identify the initial thing and the final thing, and the weighting would be e to the power minus h.
Yeah.
That would just be.
Yeah.
So that would give you a Euclidean path integral with time identified periodically
Yes.
of length 1 by t. That's clear. This plays the role of time. That's why the time. The minus rather than the I tells you it's Euclidean. But what about with this here? You see, everything continues the same up to the last step. You see, this j is a conserved quantity, so it could be inserted at any step in your path integral. So let's say insert it at the last step. What this does is take the state that you're acting on and rotate it. Right? Rotate it by the amount omega divided by t. Okay? Which is omega times Euclidean time. Okay? So in Euclidean space what's happening is that the identification is as if this thing had been moving with an angular velocity of order omega. So when you analytically continue the Schwarzschild, the Kerr solution to Euclidean space, it will exactly have the properties needed to match this partition function. Just because in Lorentzian space it was moving at angular velocity omega.
So it's this can be interpreted like since t and phi are related in the Kerr solution, whenever we analytically continue t, phi will come along for the ride.
Phi was already Euclidean, but it was moving. It was moving with t, and it was moving at the right rate to be identified with this.
t. Also
With this.
So phi was moving with t. That's why the relation comes.
That's right. That's right. And there's one confusing thing about what I told you about, that when you Euclidean continue the Kerr solution, you get a complex metric, because the dt d phi picks up an I, and that's somehow an unpleasant thing, and the rules for that are never very clear. You know, when are you allowed to consider a complex saddle point? This is a murky subject. So I mean, some people think they claim they understand it, but I don't. You know, maybe we're going too far off, but let me just say. See, what we want to do is to evaluate a Euclidean path integral for Einstein gravity, subject to certain boundary conditions. You evaluate this Euclidean path integral in the classical limit by finding a Euclidean solution of Einstein's equations with the right boundary conditions. Kerr black hole has exactly the right boundary conditions. However, it's complex. Now this is sort of irritating, because it's like this. When you're trying to do an integral here, if you find a saddle point here, does it or does it not contribute to integral? This is a very complicated subject.
Yeah, because of the boundary condition.
Yeah, there's this whole business of the theory of the steepest descents. It's a very complicated subject. I mean, there are many people who say many wrong things about it. Okay, it's a complicated subject even in the case of one-dimensional integrals, to know exactly when a saddle point of the contour contributes or not. Okay, though in case of one-dimensional thing, you sit hard enough, you'll figure it out. This is a much more complicated problem. So path integral in an infinite dimensional space, to know when a complex saddle point contributes or not, it's a complicated issue. In this case, we have lots of evidence that it does. This whole issue did not arise for the Schwarzschild black hole, by the way, because you analytically continued it. It was real. So nobody, you know, we'd have to be pretty perverse to doubt that it contributes. Anyway, this is irrelevant to our course. So let's forget it. Yeah.
ddt was a filling vector in our choice of coordinates. How would that give us a complex metric if we analytically continue t?
It's because dt continues to I dt.
Yeah.
So the dt d phi term makes it complex.
Oh, there's a dt d phi.
Right? It's not because there's an explicit t dependence, but there's a linear dt dependence.
Linear.
Okay. Fine. So let me quickly say a few words about this, and then I'll stop. Okay. Yeah. So let me say a few words about that equation. what there is a very good, okay, so suppose at the moment just we identify A by 4 with S and kappa by 2 pi with T. Of course, at this level we could have put any constants we wanted. But there are good reasons. By the way, the Euclidean argument I gave you would completely fix this. Do you remember for the Schwarzschild black hole we determined what the temperature was by going to Euclidean space and asking when the metric was non-singular? Doing something similar here, ignoring the fact that the metric is complex, will give you the identification. Kappa by 2 pi is T. Okay? So if you allow yourself to go Euclidean, there's no ambiguity. Okay? So with this identification, okay, this equation that we've seen for black holes, just by computing just explicitly in solutions of Einstein's equation, okay, tells you that black hole solutions obey the first law of thermodynamics. And sort of on the nose, right, here we didn't cheat at all. This guy just was the energy, the area energy. This guy just was the angular momentum. Omega was the angular velocity in this way that I tried to describe to you. And if you believe this Euclidean argument, kappa by 2 pi is the temperature. Okay, so you get an analysis that looks exactly right, provided you make this identification. There's great deal of evidence that this is more than a numerical coincidence. For instance, for black holes within string theory, for special black holes within string theory, we've been able to count. In string theory we have quantum theory of gravity. Just a model system of quantum gravity. Meaning it's not the quantum gravity of the real world. Simple vacua, but simple consistent quantum theories of gravity. In those theories where we have simple, very symmetrical black holes, we've been able to count the number of states, number of quantum states that go into building that black hole. And so by counting, evaluate the entropy. And every time we've been able to do it, every time in a controlled situation, you always get A by 4. In fact, there is a sophistication of the A by 4. A by 4 is the Einstein formula. In quantum gravity, there are corrections. There are corrections. And whenever we've been able to count, we get those answers, including all corrections, exactly right. Okay? So at least within string theory, we really have very good evidence that this is not just some vague analogy. It's the statement that a black hole is a thermodynamical object. A black hole is a thermodynamical object which carries a very large number of states. The entropy of the black hole is measured by the area of its event horizon by 4. Now this is an enormously surprising statement if you think about it. It's an enormously surprising statement because you say a black hole is one solution of Einstein's general relativity. Now if you think of a normal field theory, a normal classical system, the set of solutions of that theory are what we call phase space. Sorry, just a minute. Hello? Hello? Sadhu. Still in office. I'm just finishing my class. I'll come immediately after that. Pinky Didi is not there? I'll come in 20 minutes. Okay, ciao, bye. Okay, I'm going to have to terminate this very soon. Sorry, we'll do our problems on Monday. I'm sorry. Wife has to go out. Children are alone. Okay, so let's quickly say this. Okay, so where were we? At least within string theory, we have this. This really is, yeah. So why was it so surprising? It's surprising because in a classical system, a particular classical configuration, the set of classical solutions is a phase space of the theory. Then when you take a classical theory and you quantize it, roughly speaking with volumes of phase space of order h bar to the power dimension of your configuration space, to each such volume you associate one state. So to get a lot of states, you have to go over large regions of phase space. Here we are saying that one solution of general relativity carries a great deal of entropy. This is very surprising. And in fact, there's almost a clear indication that gravity is not a fundamental there. Do you know of another, by which I mean that the degrees of freedom in gravity have some substructure? Do you know of another, do you know of another theory in which something like this is true? Of course you do. It's hydrodynamics. I give you one configuration of the fluid, and that carries a lot of entropy. You can compute that entropy by evaluating the entropy density of the fluid and integrating. You know why it carries a lot of entropy? Because any one configuration of the fluid masks the fact that there are many different ways the molecules can go in order to be in the same fluid configuration. That's why fluids can carry entropy, no mystery. We started with general relativity, where we thought the metric field was a fundamental degree of freedom, like
That's true for any thermodynamic system.
But this was not thermodynamics.
No, I mean, what you said about hydrodynamics. I mean, any thermodynamic system with the same value of some macroscopic quantity.
It's true, but I said hydrodynamics, because hydrodynamics, like general relativity, gives us field equations.
Yeah.
Things are varying in space. Ordinary thermodynamics is labeled by a couple of parameters. Nothing's very surprising about it. But in hydrodynamics, you've got weights, you've got stuff like that moving around. So it looks like a field equation, but it carries entropy. And we know where that comes from, because we're masking degrees of freedom. Okay? So it must be that general relativity is like that. That Einstein's equations are actually equations of hydrodynamics of some other degrees of freedom. Okay? And there is great support for the statement within simple models in string theory. Okay? So the fact that this is the nature of gravity is actually a clue for why it's proved so hard to quantize gravity in a straightforward way. If you try to quantize the equations of hydrodynamics, you could write a textbook on it, but you'd go nowhere, because it's a stupid thing to do. You should quantize the motion of the molecules. Okay? So quantizing gravity in a straightforward way, this seems to indicate is as stupid as that. And there's a lot of support for the statement within simple model string theory. So gravity is a very interesting force, because when you do graviton scattering, in many ways it behaves like as fundamental as Young's theory. But within itself, it has hints that it's actually a thermodynamical theory. And understanding this in a clear way, that it goes beyond special examples and so on, is not yet been achieved. So there's a lot of understanding of it. It's not yet been completely achieved, and is likely, in my opinion, to lead to the real understanding of the quantum theory of gravity. Okay, let me stop here.